Explanation: a hypothesis is a clear testable statement about a population parameter. In business research, we write two competing statements. Null hypothesis H0 the status quo or no effect claim. It assumes that any observed difference is just random noise. Example: the new online advertising campaign does not change the average monthly sales. The mean sales remain $50,000. Alternative hypothesis H1 or HA the claim we are trying to find evidence for. It states that there is a real effect or difference. Example: the new campaign raises the average monthly sales to a value different from $50,000. Formulating them mathematically involves specifying the parameter, mu, p, difference of means, etc., and the direction. H0 mu equals 50,000. Ha mu does not equal 50,000, two-sided, or mu greater than 50,000, one-sided. The null is always written with an equality sign, because it serves as the baseline model that allows us to calculate probabilities. Analogy: think of H0 as a courtroom's presumption of innocence, the company is presumed not to have improved sales until proof data says otherwise. The significance level, denoted by alpha, is the threshold we set before looking at the data to decide how much risk of a false alarm, rejecting a true H0 we are willing to accept. Common choices in MBA work are 0.05, 5%, or 0.011%. If alpha equals 0.05, we are saying I am comfortable with a 5% chance of concluding the new campaign works, when in reality it does not. Alpha determines the critical region of the test statistic, the set of values that would lead us to reject H0. Mathematically, alpha equals p of type I error equals p of reject H0 given H0 is true. A manager deciding whether to launch a costly new product might set alpha equals 0.1, meaning they are willing to tolerate a 10% chance of launching a product that actually offers no profit increase. Explanation: the p-value is the probability assuming the null hypothesis is true of obtaining a test statistic at least as extreme as the one observed. Steps to calculate: compute the appropriate test statistic, ZT, etc. from the sample data. Locate its value on the sampling distribution that assumes H0. Determine the area in the tails beyond that value. That area is the p-value. Mathematically, for a two-tailed z-test, p-value equals 2 times p of z greater than or equal to absolute z sub obs, where z follows a standard normal distribution under H0. Interpretation: a small p-value, for example 0.02, means the observed data would be very unlikely if H0 were true, giving us evidence against H0. A large p-value, for example 0.45, indicates the data are compatible with H0. We have no reason to doubt it. Real-world analogy: imagine you draw a card from a well-shuffled deck and get the ace of spades. If you had claimed the deck was all red cards, the chance of pulling a black card is 0.5. Getting the ace of spades, p-value equals 0.5, isn't shocking, but getting a red joker, p-value equals 0.01, would be surprising and would make you doubt the claim. Explanation: the decision rule compares the p-value to the prechosen alpha. If p is less than or equal to alpha, then reject H0, evidence is strong enough. If p is greater than alpha, then fail to reject H0, not enough evidence. Note: fail to reject does not prove H0 is true. It only means the sample did not provide sufficient evidence against it. Example: suppose a retailer tests whether a new shelf layout changes average weekly sales. Alpha equals 0.05. Computed p-value equals 0.03. Since 0.03 is less than or equal to 0.05, the retailer rejects H0 and concludes the layout likely affects sales. If the p-value were 0.08, the retailer would fail to reject H0 and might keep the old layout until more data are gathered. Explanation: a one-tailed test looks for an effect in a specific direction, while a two-tailed test looks for any difference regardless of direction. One-tailed, for example, H(mu greater than mu0. Critical region is only in the upper tail. The p-value is p of z greater than or equal to z sub obs for a z-test. Two-tailed, for example, H(mu not equal to mu0. critical regions are in both tails. The p-value is 2 times p of z greater than or equal to absolute z sub obs. Effect on p-values. For the same observed statistic, a one-tailed test yields a p-value that is exactly half of the two-tailed p-value, provided the statistic is in the direction hypothesized. Practical analogy. If a chief executive officer claims the new pricing strategy will increase profit, a one-tailed test is appropriate because a decrease would be irrelevant to the claim. If the chief executive officer only says the strategy will change profit, a two-tailed test is needed. The most common test statistics are 1. Z-statistic, standard normal, used when the population variance is known or the sample size is large, n greater than or equal to 30, so the central limit theorem applies. Z equals x bar minus mu 0 divided by sigma over square root of n. Under H0, Z follows a normal distribution with mean 0 and standard deviation 1. 2. T-statistic, used when the population variance is unknown and the sample size is small. The sample standard deviation S replaces sigma. T equals x bar minus mu 0 divided by S over square root of n. Under H0, T follows a student's T distribution with degrees of freedom equal to n-1. Both distributions are centered at 0 when H0 is true, which allows us to calculate tail probabilities p-values. The T distribution has heavier tails, reflecting extra uncertainty from estimating the variance. Business example. A startup wants to know if the average time to resolve a customer complaint is less than the industry benchmark of 48 hours. They collect a small sample, n equals 12. Because the true variability of resolution times is unknown, they use the t-test. A type 1 error occurs when we incorrectly reject a true null hypothesis. Its probability is exactly the significance level alpha. Probability of type 1 error equals alpha. A type 2 error happens when we fail to reject a false null hypothesis. Its probability is denoted by beta, and the test's power is 1 minus beta, the chance of correctly detecting a true effect. Relation to p-value colon. The p-value itself is not the probability of a type 1 error. It is the probability of seeing data as extreme as ours if H0 is true. If p is less than or equal to alpha, we are willing to accept a risk of alpha of making a type 1 error. A smaller alpha reduces the chance of type 1 errors but usually increases beta, more type 2 errors, because the rejection region shrinks. Analogy colon, think of a smoke alarm. Setting it very sensitive, low alpha, means you rarely miss a fire, low type 2, but you get many false alarms, high type 1. Setting it less sensitive, high alpha, reduces false alarms but risks missing a real fire. Explanation. Below are 5 typical MBA-style exam questions that test understanding of null hypotheses and p-values. 1. Conceptual. Define the null and alternative hypotheses for a study investigating whether a new training program changes employee productivity. Indicate which hypothesis contains the equality sign. 2. Computation. A sample of 40 stores shows an average sales increase of $3,200 after a promotional campaign. The known population standard deviation is $10,000. Test at alpha equals 0.05 whether the campaign has increased sales. Show the test statistic, p-value, and conclusion. 3.1 versus two-tailed. Explain why a manager claiming the new supplier will reduce costs should use a one-tailed test, and what would happen to the p-value if a two-tailed test were mistakenly used. 4. Type I/II. If a company sets alpha equals 0.01 for a new product launch decision, what is the probability of a type I error? Discuss how increasing alpha to 0.05 would affect the risk of type II error, assuming all else equal. 5. Interpretation. In a hypothesis test, the p-value is reported as 0.18. Explain in plain language what this number means for the null hypothesis and for business decision making.